There are forces in the world that people seem only able to accept. Time does not flow backward, death is inevitable, and an apple will always fall to the ground. But it turns out that physicists already have quite a few ways to keep an object suspended in the air without any mechanical support. Let's take a look at them. It would seem that counteracting gravity using magnetism is very easy. But in reality, creating stable equilibrium is not that simple. Earnshaw's theorem prohibits static paramagnets and ferromagnets from producing stable levitation without additional conditions. Rotating two permanent magnets, even by a very small angle, will cause them to turn toward each other with opposite poles. Fortunately, there are several ways to bypass this restriction. One of them is to place a diamagnetic material in a magnetic field. Unlike a paramagnet, it becomes magnetized not along the external field, but in the opposite direction, and nothing prevents it from stably levitating in the air. And with small deviations from the equilibrium position, the diamagnet's own field can adjust itself to bring it back to equilibrium. It's not hard to find a diamagnet. This behavior is typical for many substances, including organic compounds. So, in sufficiently strong fields, living creatures can levitate as well. There are known experiments where, with magnetic fields of tens of Tesla, frogs and mice were sent flying. In a similar way, stable levitation can be achieved using superconductors, materials that, when cooled to very low temperatures, completely lose electrical resistance. When in a superconducting state, the sample expels or almost expels the external magnetic field applied to it from its volume. That is, from the observer's point of view, it behaves like a perfect diamagnet, which not only becomes slightly magnetized in the opposite direction, but as if it were a magnet of equal strength with opposite polarity. Thanks to this, superconductors require, on average, less powerful fields for levitation compared to real diamagnets. The trade-off, however, is that the material has to be cooled to temperatures close to absolute zero to bring it into a superconducting state. And that, let me remind you, is minus 273.15 degrees Celsius. Another way to create stable levitation is to use non-static magnetic fields, to which Earnshaw's theorem does not apply. For example, below you can see an invention from the 1980s, a kind of magnetic top. A stationary bowl-shaped magnet supports a spinning magnet shaped like a top above it, with its field. Finally, you can stabilize levitation using feedback, that is, by monitoring the position of the object and adjusting the strength of the magnetic field, so that it constantly keeps the object from slipping out of place. This method is used by Maglev trains. Maglevs do not touch the rail, but levitate above it, which makes them the fastest type of public transportation. The only thing that slows them down is air resistance. In 2015, a Japanese Maglev set a record speed of over 600 kilometers per hour during tests. And the Maglevs being designed for vacuum tunnels will probably move an order of magnitude faster, covering up to 6,000 kilometers in an hour. In the summer of 2017, the German company ThyssenKrupp demonstrated the multi-elevator, which operates on the same principle as Maglevs, meaning it levitates. Such an elevator is capable of moving not only vertically, but also horizontally. This means that it is possible to design non-linear shafts where cabins can overtake each other and move between different parts of the building, increasing the system's throughput. Another way to achieve levitation is to use the pressure of light. In 1986, American physicist Arthur Ashkin and his colleagues demonstrated the operation of the so-called optical tweezers. If you try to work with microscopic objects, cells, proteins, molecules, and even smaller particles using regular tweezers, such an experiment is unlikely to succeed. A mechanical tool is too rough for this and will only destroy the system being studied. The scientist figured out how to replace mechanical levers with an intense laser beam, which uses the pressure of light to hold microscopic particles without affecting their internal structure. To achieve levitation of an object in such tweezers, the laser beam is focused through a microscope objective. As a result, the beam forms a waist, a narrowing, where the intensity sharply increases from the edges of the beam to its center. Ashkin's development played an important role in the study of many biological processes, particularly molecular machines, research on which won the Nobel Prize in Chemistry in 2016. Among other things, with the help of optical tweezers, scientists observed how a kinesin molecule walks along the surface of a sample. This is the very image that people caption on social media. This is what happiness looks like. A myosin protein molecule walks along an actin filament, dragging an endorphin sphere into the inner part of the brain's dark cortex, which is responsible for happiness. But, as you already understand, that's far from the truth. Not myosin, but kinesin. And not along actin, but along tubulin microtubules. Not an endorphin sphere, but a sack of proteins from the ribosomes. And not in the dark cortex, but inside the cell. But here's what's more interesting. Using optical tweezers, they even measured the force with which it can pull objects. For this, researchers attached the end of the molecule to a microscopic sphere suspended in an optical trap and measured how far the molecule could pull the sphere from its equilibrium position. And in one of the Russian projects, they developed a combined setup that integrates a laser scalpel and tweezers. With this setup, scientists were able to cut the embryo's shell at early stages of division and extract the polar body with tweezers. Studying the polar body allows them to assess the condition of the embryo, particularly for genetic abnormalities. And American scientists have learned to create three-dimensional color holograms by illuminating a small particle, which they moved with optical tweezers at a speed of almost 2 meters per second. Thanks to the persistence of vision, the light trail merged into a single color image. With the setup they built, the authors of the article managed to play a three-dimensional video recording at a rate of about 13 frames per second. Each frame in this case consisted of more than 16,000 colored dots, and the flickering of the image was almost imperceptible to the naked eye. The scientists also obtained more complex images by increasing the exposure time to a minute. Another type of levitation is acoustic. When coherent acoustic waves with a constant phase difference over time overlap, it is possible to form a standing wave. This is a state of oscillation in which the regions of minimum and maximum amplitude do not move, and the wave seems to freeze in space. This creates static regions of increased and decreased pressure. This can be used for levitation by placing an object, whose size does not exceed the wavelength, in the region of minimum pressure. The increased pressure around it will prevent it from falling and stabilize it against small sideways movements. If you smoothly change the phase and amplitude of the sound waves, you can change the position and depth of the acoustic traps, and thus make objects not just float in the air, but move through space. So, in January of this year, Japanese engineers demonstrated a device in which a balloon controlled by ultrasonic emitters became an input-output interface. Experimenters are still working to overcome the technical limitations of acoustic levitation. A couple of years ago, British engineers taught their device to bypass obstacles by placing a structured plate with cavity sizes on the order of the wavelength in front of the emitters. Because of this, the phase of each wave changes so that when they are combined, the resulting sound field bends around the area near the emitters. And shortly before that, other British researchers made an object larger than the wavelength levitate. To do this, they placed 192 ultrasonic transducers on the surface of a spherical sector and, using them, instead of a regular standing wave, created a set of sound vortices with opposite directions in the air. Such a configuration of the sound field was able to hold a polystyrene ball with a diameter of 1.6 cm, which is almost twice the wavelength. Finally, a third group of British engineers in the spring of 2020 implemented hand-controlled levitation. Information about its position was read by an infrared sensor and transmitted to the ultrasonic emitter arrays. In response, the latter adjusted the emitted waves and moved the flying ball in the direction indicated by the finger. For demonstration, the researchers presented a prototype arcade machine that requires the player to guide the ball through rings. For levitation, not only oscillations that travel through the air can be used, but also vibrations of solid objects. In a similar way, it is possible to make a layer of viscous liquid levitate above a layer of air. If the support on which the vessel is placed oscillates rapidly, the resulting vibrational forces prevent droplets from forming on the lower surface of the liquid, and it stops flowing downward under the influence of gravity. In September 2020, French physicists discovered that this method can not only make a liquid float in the air, but also allow its lower surface to be used for sailing. just like the upper one, and they sent small boats cruising along the underside of the water. The upside-down boats mirrored the behavior of objects that floated in the usual way on the upper surface of the levitating body of water. And as a final illustration, let's take a look at these shots of levitation metallurgy, which we featured in one of our previous episodes. As you can see, levitation is now almost commonplace in the modern world. It has already proven itself both as a tool for scientific and technical work, as a basis for transportation, and as a means of entertainment. The flight of human thought cannot be stopped, and most likely, in the coming years, we will see the realization of new ideas for hovering in the air. Or maybe some ideas will be suggested by past civilizations. In any case, we will definitely show you all of this. Turn on notifications so you don't miss anything. See you on Cremola.